All right, in this video, I'll overview the procedure sections of Lab 3. I'll try to be brief because most of the details you'll need are contained in other videos linked within these sections. Okay, let's go to procedure section A. This is where you'll carry out your observation, which is actually something you should have begun 1 to 2 weeks ago. You should have most of your data back by now. Here's a link to a tutorial that will show you how to put in this monitoring observation, and that's what you're going to be doing. You're going to be monitoring one of the 4 gas giants, which means observing it repeatedly. You'll be observing it once a day for a period of 1 to 2 weeks, watching a particular moon go around the planet. After you've watched the tutorial, we have a few reminders here that I'll let you review once you've gotten that far. Let's go down to procedure section B, part 1. So once you have your observations back, you're going to measure the distance between the planet and the moon in each of your images. There's a tutorial here showing you how to do that. Then down here, indicate which moon you measured. If you observe Jupiter, the moon that you'll measure will be Ganymede. If you observe Saturn, it will be Titan. If you observed Uranus, it will be Oberon. And if you observe Neptune, it will be Triton. You then put your measurements in this table. The date of the observation, measured in Julian days, will be here. And the angular separation, measured in arc seconds, will be here. Sign your name down here to attest that you collected these data yourself. Then we can move on to procedure B, part 2. Once you have these measurements of how far the moon is from the planet at different times, we can quantify the orbit. In other words, we can measure the semi-major axis of the orbit, how big it is, and the orbital period of the moon, how long it takes to go around. To do this, you'll go to our graphing website here, which I already have loaded here. Change the option to moon. You'll enter your measurements here, and then you'll adjust the model to agree with the measurements. How to do this is described in this tutorial. And then once you're done, you'll download your graph onto your computer, then upload it to WebAssign here. It should look something like this, where the distance from here to here is how far the moon gets from the planet. That's the semi-major axis. And 2 of these cycles is the orbital period, where one cycle corresponds to the moon's motion on one side of the planet, and the other cycle corresponds to its motion on the other side of the planet. You'll input your measurements here. The semi-major axis, you'll measure in arc seconds on the sky, and the orbital period, you'll measure in days. Okay, let's go to part 3. Now in this part, you're going to convert your semi-major axis from arc seconds to astronomical units measured at the distance to the planet. You're going to convert your orbital period from days to years. And then once you've done these 2 things, you can very easily calculate the mass of the planet using Newton's form of Kepler's 3rd law. First, let's convert the semi-major axis from arc seconds to astronomical units at the distance to the planet. And for that, you'll need the distance to the planet. You can get that from Stellarium for the time of one of your observations. It's listed here under distance. Be sure not to use distance from sun. Use distance, that's the distance from Earth. Now I should note that in the next lab, you'll learn how to measure this distance independently using a technique called parallax. But for now, we'll just grab that distance from Stellarium. So we need to figure out the conversion factor from arc seconds measured in our image to a physical distance at the distance to the planet, measured in astronomical units. So to do this, I want you to imagine a giant ruler out there in space at the distance to the planet. And that ruler is measuring astronomical units, or some fraction thereof. And this ruler, when we take a picture of it, imagine that it subtends 1 arcsecond in our image. So if we can figure out how big this ruler is, then we'll have our conversion factor from arcseconds in our image to astronomical units at the distance to the planet. And we can figure that out using this geometry, which should look familiar because we used the same geometry in the last lab, and we'll use it again in future labs. So what does this geometry tell us? It tells us that the angular length of our ruler, 1 arcsecond, as a fraction of 360 degrees, is going to be exactly the same as the physical length of our ruler, measured in astronomical units out at the distance to the planet, as a fraction of the circumference of this big circle centered on Earth. And we see that down here. The length of that ruler divided by the circumference is equal to the angle, 1 arcsecond, divided by 360 degrees. Now, the circumference of any circle is 2 pi times its radius, and the radius of this big circle is the distance between us and the ruler, and hence between us and the planet. So we can substitute for circumference 2 pi times the distance to the planet, and we can solve this equation for the length of the ruler. Then all we have to do is input the distance to the planet, which you've already looked up in Stellarium, and the angle, which is 1 arcsecond, but be sure to convert it to degrees first. You can then calculate the length of the ruler in astronomical units. You can input that there and show your work here. And then we have our conversion factor. We can take the semi-major axis that we measured in arcseconds and multiply by the length of the ruler, measured in astronomical units. And that will give us the semi-major axis measured in astronomical units. You input that there and show your work here. And note, it should be a small number. The astronomical unit is the distance between the sun and the Earth. The distance between a planet and a moon should be much less than 1 astronomical unit. Next, you'll want to convert the moon's orbital period from days to years, which you do by dividing by 365 days in 1 year. You can input that here and your work here. Then you can use Newton's form of Kepler's third law to calculate the mass of the central body of the planet. And we describe how to do this in one of the background sections. But once you have the semi-major axis in astronomical units and the orbital period in years, it's very simple. You cube the semi-major axis and divide by the square of the orbital period. And what you'll get is the mass of the planet, the central body, and it will be in solar masses. So again, this will be a small number. The mass of a planet is much less than 1 solar mass. You input that there, show your work here. And finally, I want you to convert that mass to Earth masses. The mass of the sun is 333,000 times the mass of the Earth, and you can use that to do your conversion. Put the mass of the planet in Earth masses here, show your work here, and then Google the true mass of the planet and calculate your percent error. Now, this is a tricky observation to make. Small errors in the semi-major axis and the orbital period pile up once you cube them and square them. And so typical percent errors may be 10, 20, 30, even 40 or 50%, just to set your expectations. Discuss sources of error here, and then we'll move on to procedure section C. This section begins with a tutorial on how to measure the angular diameter and phase of Venus for multiple locations in its orbit, and how to use these to distinguish between the geocentric and heliocentric models of the universe. We also describe how to do this in one of the background sections. After you watch the tutorial, there are a few reminders, and then you input your illuminated angular distances, that's the short distance, here, your angular diameter, that's the long distance, here, and the phase, which is given just by their ratio, here. Another honor code pledge there. And then you go to the graphing website, and this time go to the Venus option. You'll input your measurements here and make the necessary plot. You'll download it onto your computer, upload it to WebAssign here. Then we ask you, are your measurements more consistent with the geocentric or heliocentric models of the universe, and why? And then you can discuss your sources of error here. Okay, that's it for this overview video.